The nice thing about the formulation is because it's not done in a kind of integer programming way, we don't have to like framing the constraints exactly kind of naturally falls out of the representations we're using. So in this specific case, we would just limit the set of objects considered for the tree search. So basically at a very high level, there's a set of objects and now you sweep along it and you kind of branch on each of the object, whether you can succeed or fail. And there are more details about that. But if there are certain constraints that a certain agent cannot address a certain task, maybe it's out of range or it's out of the time window, then we just wouldn't consider that object in the tree search for that agent. And then the rest of it should just hold.
All right, awesome. Thank you very much.
Thank you. Thank you for having me.
Next, we have inner attention modeling for flexible teaming of heterogeneous multi-robots using multi-agent reinforcement learning. Do we have Chao?
Yes, I'm here.
Hi. So could you take a sentence or two to summarize your work, Chao, and then we can dive into the questions?
Yeah, okay. This research is actually motivated when robot is doing some tasks like research, like a search and rescue. The robot may have different tasks to do. For example, like rescue heavily injured victim and leading victim in good health to a safer place. But sometimes the robot can be broken, or sometimes the task requires different type and ability of the robot. In order to solve these issues, we have used the inner attention mechanism to let the robot can cooperate with the proper type.
Okay.
Proper type robot members who participate in the proper tasks.
Okay. So one of the first questions here is, could you provide the intuition behind how the reward is chosen for this particular problem?
Pardon?
Could you provide some intuition behind what sort of reward is chosen for this problem such that it will incentivize the kinds of behaviors you want?
That means the word choosing.
Yeah, the reward function that you have designed for this problem.
Our reward function. For this part, because this method is mainly based on the reinforcement learning method, so there is the general reward about the collision to the obstacles and walls, and there is also reward to analyze the distance between the robots and the victims.
Okay.
But there's also two base rules. The first one is that robot will rescue the closest victim to win.
Okay.
And the second one is the robot only rescue the closest victim if this robot isn't occupied by other tasks.
Okay. Actually, thanks for that answer. It sort of answers the next question too, which asks about how you incentivize to pay attention to the right ones. Okay. All right. So Ragesh, before you move on to the next one, I think Venkateramana has his mic working now. So if you can switch to him and then move on to the sixth paper, that'll be good.
Can you hear me, guys?
No? Yes. We can hear you, I guess. So Venkat, so yeah, this is Venkat's paper. It's on Apollonier's allocation algorithm for heterogeneous pursuers to capture multivariables. So Venkat, can you give us a brief summary before you go into answering the questions? So yeah, the question. Yeah, give a brief summary and then I'll start with the questions.
Sure. So yeah, here in this work, we are interested in assigning for source to evaders in a multi-purse or multi-evader setting. We have large number of person, large number of evaders. Is there an algorithm to dynamically assign for source to evaders that they can pursue? And in this case, we have assumed simple motion for the agents, and we assume the port source are constant bearing just so that the problem is tractable. Since it is constant bearing, we have realized that we can use geometric arguments to come up with this allocation algorithm using Apollonier circles. the algorithm that we had come up with guarantees finite time capture, though we are still working on getting guarantees for the capture time. So that's where we are right now with this paper.
So yeah, the approach that you guys have taken is an interesting one. So one of the questions that came up was like, is this approach related to the Warner diagram kind of an approaches that people have generated, or is this the approach that is a more generalized version of that?
So it is kind of related, but the definition of Apollonius circle is kind of restrictive. It's kind of defined only for the pair, the pursuit evador pair. But Warner diagram is generalized, defined for generators, like it could be arbitrarily any number. So I would say it is related, but I think it's restrictive. It's not completely capturing what Warner diagram is capturing for like multiple agents. It's still for two agents, and in that sense, it will be kind of different. Yeah, I hope that answers the question.
Yeah. Another question that's out there is like currently it is a pairwise evader consideration that you, I mean, which is more, I think it was unicycle dynamics that you guys are considering in the, yeah. So, I mean, what would change if you had more complex dynamics, like more nonlinear dynamics? Like would the approach would you stay the same? I guess you have.
No, I think you have to modify the Apollonius circle itself, because right now the Apollonius circle assumes, again, the way the algorithm has been developed, it has assumed holonomic dynamics. So which means the moment you have turn radius constraints, for example, which is like more complex dynamics, you cannot use Apollonius circles, and you have to, again, at the end of the day, Apollonius circle kind of captures safe reachable area, which was put forth by, I think, Tomlin and others. And there is a work by, I think, Postlewaite that talks about safe reachable area in the case of turn radius constraints. I think that's where we should be kind of heading towards. And the Apollonius circle then becomes a concave curve. It's not convex anymore.
Okay.
And I think the challenges.
Yeah, thanks. So one final questions out there is like, what would be the scenario when you have slower pursuers compared to the evaders?
So for slower pursuers, it's kind of proven that capture cannot happen with slower pursuers. Though the slower pursuers can take positions just to restrict the evader's motion. So maybe it's kind of interesting to see that, let's say we have a heterogeneous team of faster pursuers and slower pursuers. We can use the slower pursuers sort of guards. Beyond that, they cannot go into capture. But that's kind of interesting extension that we can think about.
Okay, thank you.
Yeah.
So next is Benjamin Revere and group from Caltech. So the paper is titled "Class: Global to Local Safe Autonomy Synthesis for Multi-Robot Motion Planning with End-to-End Learning." So is Benjamin out there, or somebody from yes, hi Ben. Hi Ben. Hi. So can you just give a brief few sentences about your paper, and we'll come to the questions.
Sure, Ragesh. Thank you for having me. So our paper is about doing imitation learning on a centralized motion planner, but then masking non-local information. So basically, we transition automatically from a global local motion planner to a motion planner that imitates a global motion planner with only local information. And we can, by using some control theory, we can guarantee that it's safe. And by leveraging these learning representations, compact learning representations called deep sets, we have a very compact model that can run very quickly on microcontrollers for drones. So I think that's kind of the quick explanation of what it was.
So thanks, Ben. So the first question out there is, can the algorithm be generalized to different types of multi-robot tasks, not really just related to motion planning?
That's a great question. That's actually what we're working on right now, is kind of, because one way to view GLASS is kind of just a wrapper on any centralized algorithm to turn it into a local, like a decentralized algorithm, so you can scale with number of robots. So right now we're working on like heterogeneous swarm games. So we're like, and we're trying to generalize strategies and learn them through imitation learning, which I like for the stability of the learning process. I'm impressed at the previous works that were able to like do reinforcement learning on multi-agent teams stuff. I think that's pretty challenging.
Okay, thank you. Another question out there is like, how do you pick the convex combination parameter, which is basically a trade-off between the safety and performance, if I remember right?
Right, exactly.
Because you don't want to compromise on safety, and definitely, I mean, usually people do that as a constraint because that's something that you never want to violate, and never as an optimization problem. So yeah.
Right, exactly. So the way that we pick our convex combination is we treat the neural policy as so it's, as you said, it's a convex combination of the neural policy and a barrier function. And so we use invariant set theory with where we create a bunch of sets between every pairwise interaction of the robots and the obstacles to guarantee no collisions. And the convex parameter is chosen basically by, in the worst case scenario, if the neural policy was to push against the gradient of the safety function, the convex parameter would scale the barrier and the neural policy such that the barrier would be stronger than the neural policy. So that's how we guarantee safety.
Okay, thanks. So Harish, I think you can take off now.
Thank you. So next up, we have a trust-aware emergency response for a resilient human swarm cooperative system. Do we have Jiang Pang here?
Yeah, I'm here.
Okay. All right. Thank you. Could you please summarize your work before we dive into the questions?
Yeah, sure. In this paper, we envision a human swarm cooperative system, and the swarm, the human, serve as the operator to monitor and guide the execution of the robot swarm. However, uncertainty happen to decrease swarm performance because of the consensus behavior of the swarm. One 40 robot could mislead the whole team. Cause their mission failure. And we get inspiration from trust in human-human interaction. In this paper, we use trust between human and robot team to facilitate human swarm collaboration. Okay.
Okay, thank you. So the question we have here is, so you have these two different quantities you call the trust level you have for each agent, and you also have this quantity of weights that you associate with respect to different agents' information as you get them. Can you speak a little bit about how these are chosen or learned? How would you compute these weights?
First of all, G is the trust level, and W is the weight for updating each robot's status. And G actually is estimated by human operator, so it's not calculated. So it's provided by the human operator. And W is updated using the weighted mean subsequence reduce algorithm.
Okay. Another question is you speak about how if there are failures for certain robots, you will no longer take information from them in order to not corrupt the information that you're accumulating or assimilating. Could you speak about, do you make the assumption that the failures are detected automatically, or you have perfect information about when a robot fails?
Yes, in this paper, the failure can be detected automatically by the human operator. So the human operator could assign the trust level for each robot. So I think that's how we detect the failure.
Okay, that makes sense. All right, thank you very much.
You're welcome.
So our next speaker is again from CMU, and the paper is from Getty's group. I think the paper is online connectivity aware dynamic distribution for heterogeneous multi-robot systems. Chantley Lane, is Chantley Lane in the audience right now?
Can you hear me?
Yeah, yes. So can you briefly go over the, so you know the drill, so can you just briefly go over the paper and before you come to the questions?
Sure. So briefly, this project is about how to dynamically distribute and allocate the robots at both planning and control level in a dynamic system for heterogeneous robot systems. So basically, and where a big part of this project is taking the connectivity maintenance into considerations. So basically, a big part of that is that if some robots are serving, like standing in the middle of the surface connectivity nodes, they're not actually contributing to the performance of the tasks. So how to drive the whole system to a more desired configuration so that the overall utility can be maximized. without making too much changes, like adaptively, basically, is the main idea of this project.
Okay, so the first question you have from the group is, yeah, I mean, this community, it's really an interesting framework. So do you guys have some really a good example where you can, I mean, the framework is a little abstract. So do you have a direct example where this framework can be directly applied without much change? I mean, have you considered some direct examples to work on?
Yeah, so if I understand this question correctly, I think it means besides the target covering tasks that's discussed in the paper,
yes,
is there any more like tasks specific or like task missions that this framework can be applied on?
Right.
The quick question is yes. This framework is very general. So whatever kind of task specific controller you have for your system, you can always integrate it into it. We use target covering because it's the easiest way to visualize it. But say if you want to have say you want to encircle a target, or you want to form, like do any formation control, you can always have that in your primary controller part or task specific controller part. And it doesn't affect the whole framework at all. You can easily integrate it into it. It's not the main idea that discussed in this paper, because it's not focusing on that. But yeah, I think it can be readily applied to any kind of tasks if you have the controller in hand. Yeah.
Okay, thanks. Thanks, Jamie. So we have another paper again from Pradap's groups from UMD. It's titled Improved Resilient Coverage Maximization with Multiple Robots. Is Ishant Rabin?
Yeah.
Is here. Oh, did I pronounce your name right? Sorry if I made a miss. So can you give a brief sentence about your paper, and we can go into the questions after that.
Yeah. So in this work, we worked on maximizing coverage of multiple robots when some of the robots may fail. So what we did is we studied the existing literature and identified some limitations of the previous works, like low accuracy and high running time. And we proposed two classes of algorithms that that provide higher accuracy and lower running time with respect to the previous works. Yeah.
Okay. So the first question you have, right. So the approach to solve the resilient problem depends on the selected robot candidate trajectories. So is there a generic way to generate the candidate trajectories for the coverage problem? So basically I'm guessing what the person wanted to ask is like, in general, trajectory generation is basically it's an infinite dimensional problem, because trajectory space is an infinite dimensional space, and you can only generate so many fewer samples. So you can only generate so few. So how do you efficiently generate sample trajectories that ensure that you can actually perform your task?
Yeah. So one way to generate trajectories is to impose kinodynamic constraints, like giving bounds on the acceleration and velocity of the robot, such that the motion of the robot is smooth with respect to the previous trajectory. So this kinodynamic constraints works well in case the planning horizon is short enough. But in our work, the planning horizon the framework was defined such that the planning horizon can be assumed to be long. So we used a set of given trajectories in our formulation.
Okay, thanks. Right. So so thank you, Sean. So we'll go into the next guy. So right. So the next is from Philip Dame's group, I think from Temple University, The paper is Distributed Multi-Target Search and Tracking Using Coordinated Team of Ground and Aerial Robots. So Jun Cheng, if you are in the audience.
Yeah, hi, can you hear me?
Yes. So can you just
great.
give a brief sentence about your paper, and we continue questions?
Yeah, no problem. Thanks. So in this paper, we're trying to find a distributed coverage control solution for a team of heterogeneous multi-robot team, and we assume that the team is composed. The team has a ground robot team and a air robot subteam, and we would like to take advantage of both ground robot and air robots because we assume that ground robots have heavy payloads and a long battery life and more powerful computational resource. And we assume that the air robot have more mobility and changeable field of view and all these advantages. And we would like to have these two sub-teams to cooperate with each other to track targets in an open and convex area. And we found that by cooperation of these two heterogeneous multi-robot teams, the overall tracking efficiency is more is greater than just mix these two teams together.
Okay, thanks, John. So your first question, I think your question is, how often do the robots need to exchange information with their neighbors? Is there a common frame preference assumed for all the robots?
Yeah, so for the target estimation for each of the subteams, we're using the method, the filter called the probability hypothesis density filter, which is also a target state estimation estimator that is similar to Bayesian filter. So in this recursive estimation process, in each of this process, we will have a few data exchange process. And as this recursion keep processing, and there's the data exchange process is happening like a few times, like 4 or 5 times in a recursion. And yeah, we do have need all robots to have a global to have their knowledge of position in a global coordinate system. And yeah, the most common way is to use a positioning system like GPS or the motion capture system indoor.
Okay, so thank you, John. So before we move to the next paper, just a small thing. So I don't know if everybody's aware that there's a Google Doc where everybody could post papers or post your questions, or you could actually also post your questions on the chat. So in the interest of time, we won't be able to actually take in all the questions live, but if the authors could go into the Google Doc and answer some of those questions which are not answered, would be really great, because that would be great. And if the time permits, we might keep that questions later, but we don't, I mean, in the current scenario, we don't see we have enough time to do that. So please go to the, so if you don't have access, if anybody do not have access to the Google Doc, please go to the website and you have the link to the Google Doc. So please go to the Google Doc and answer those questions that concerned with the paper if it is not answered in the session, and so that way everybody has answers to all the questions and everybody is in the same page. Thank you. So the next paper is from Ryan Williams' group from Virginia Tech. The paper is monitoring over long term task allocation and coordination for multi-robot sensing. Zheng Liu is...
Yes, I'm here. Can you hear me?
Okay. Did I pronounce your name right?
Okay, so let me first introduce our work. So in this paper, we focus on how to monitor a slowly evolving environmental process, because we want to save energy. So that means we cannot send our robot frequently to collect information to build the environmental model. So we couple the sensing location and the sensing time together, and also set the budget for the deployment times and actual deployment cost. And finally, we formulate the problem as a submodular maximization with mutual and life cycle constraint and solve it with constraint with guarantees. Okay, thanks.
Okay, so the question you have is the set of time indexes picked by the use? Is the set of time index picked by? Is there a set of time indexes picked by the user, and how does the algorithm complexity scale with the cardinality of that set?
No, because the time is selected by the algorithm, because once we set the constraints, such as if we set the constraint such a constraint as how many times we want to collect the information from the environment, that is the constraint. And then based on this constraint and the solution, we will load exactly in the sensing time. So this sensing time is not selected by the user. The second one is because this algorithm can be implemented in parallel. So if we do it in parallel, so the complexity is n raised to the power of 2, where n is the cardinality of our ground set.
Okay, thank you. So moving to the next paper, it is from Stephanie Gill's group. So the paper's titled Active Rendezvous for Multi-Robot Post-Graph Optimization Using Sensing over Wi-Fi. I think it's Wing Wang. Is he the author?
Yep.
Okay. Yeah. Can you describe the paper a little bit? And we'll go to the questions after that.
Yeah, sure. Thank you, Rakesh. So for this work, we're focusing on the multi-robot exploration task. We utilize the communication itself among the robots to obtain the relative direction information, which is purely independent of the map quality and also other sensors quality. And it's also in the way of distributed. We utilize the utilization of the communication means just minimal PIM packets without actual data exchange, and there's no point-to-point communication required. And it's also work naturally in the light disabled environment. So we deploy this information on demand into the post-graph optimization as a backend optimization framework by actively enforcing the rendezvous between robots or paired robots and detecting the outlying measurement or edges in the graph. We also conducted the extensive simulation and hardware experiments in nearly 3,000 square meters testbed, which shows a great ground truth error reduction in trajectories. I think that's kind of brief summary of our work.
Okay, so it's actually a multi-robot SLAM work, I'm guessing. So the question it's out there posted as like, so how do you decide? So you need to actually communicate with your neighbors. So how do you decide whether to, like, once your trajectory error goes above the shore, whether the robot has to move or has to still wait to have a plan? Because there is no guarantee that you always have a neighborhood set, right? So there could be cases like you never get a neighbor at all. Although in practice you may not see that, but in general it may not be true. So how do you go about solving that problem?
Yeah, I think in our study of previous work, there's several cases. So in one of the major cases, if you just go forward, you continue to explore, you may suffer from unrecoverable errors because for post-graph optimization, you're kind of finding the mean among all the observations, right? So if you error goes high and it will just explode at some point and it can never recover, which leads to cascading failure in the optimizations, which is bad. So in our implementation, we kind of just pause it. We don't want to go any higher than threshold because we find some balance point that's before the explosion. But in reality, you have a lot of way to find a balance, right? Because it's really depend on the scale of the task and also the area of the environment. Like in our experiments, even it's pretty large testbed, but because of it's using general Wi-Fi signals, it can reach every corner of the 3,000 square meters testbed. So I think most case we will see there's no available robots is is sometimes all the available robots are paired with some other agents who need help. So maybe cannot find any available robots. You have to just wait. But as I said, it highly dependent on the scale of the task.
Okay, thank you, Shane. Harish, I think you can take over from now.
All right, thank you. A quick housekeeping comment before we move on. So the authors, if you can monitor the Zoom chat, that'd be great. I think there are some questions that come up and we haven't had a chance to talk about them when we discuss the paper. So feel free to submit the answers there as well. And you, of course, for everybody else, feel free to use the Zoom chat also as another stream in which you can submit your questions. Okay, next up we have Sharan Raja. Sharan, are you here? Could you unmute your mic, please? I don't think we could hear you.
Oh, yeah. Can you hear me now?
Okay, yes,
yeah.
We can. Thank you. Could you talk a little bit about your work before we jump into the questions?
Yeah, sure. So in this work, we try to address communication constraints in the context of running a decentralized task allocation algorithm. So just to give a little bit of historic context, most algorithms, task allocation algorithms consider an idealized communication setup, but this assumption breaks down when you deploy multi-agent systems in ad hoc networks. And so you run into issues like message interference and bandwidth limitations. And this has been studied extensively in the communication networks community. But the question we ask here specifically is, given that you know you're going to run a specific algorithm here, for example, CBBA, can you come up with a communication protocol, or can you co-design a communication protocol that is better than a generic communication protocol that is agnostic to the algorithm? And so the way we do this is by using information about the message that you're sending, which encapsulates the knowledge about the algorithm, and also local communication graph features to selectively allow agents to speak over the shared medium.
Okay, thank you. The question we have here is, could the connectedness, for example, if it's measured by the second eigenvalue of the graph location, if you are considering a two-hop neighborhood, can that serve as a sort of proxy that's convenient for the features that you're thinking about? Or
Right.
If not, what's the difference?
Right. If I understand correctly, the eigenvalue of the graph Laplacian basically gives you how connected the graph is, right? So, but specifically in this case, what we are looking at is when you're running CSMA, which is the MAC layer protocol, you want to know how many agents are scheduled at the same time as this agent. So this directly translates to the problem of finding maximal independent set. And so I looked at a few papers online, and there are works which show there is a bound on the size of the maximal independent set based on the eigenvalue of the graph Laplacian, but it's unclear how tight or how loose this bound is. But that's a really interesting question, and it's something that we can look toward.
Okay, awesome. Thank you. So in the interest of time, we will stop here. But if you have additional thoughts, feel free to post it on the Google Doc, and we can continue the discussion there. All right. Next up, we have a resilient and energy-aware task allocation framework for heterogeneous multi-robot systems from Gennaro.
Yes.
Hi, Gennaro. Could you take a couple of seconds, sorry, not seconds, I suppose, a couple of sentences to summarize your work before we dive into the questions?
Yeah, sure. So yeah, in this work, we consider the multi-robot task allocation problem when we have an explicit description of the heterogeneity of the robots with a specific goal of rendering the assignment resilient to external disturbances as well as like failures of the robots. And so the key idea is that of interpreting the allocation of tasks to robots as a different prioritization that the robots have at performing different tasks. And so thanks to this formulation, we are able to formulate in the end an optimization program that can be run online and adaptively changing the allocation based on the environment and robot states.
Okay, awesome, thanks. So the first question we have here is, could you speak a little bit more about, or the intuition behind the bipartite graph that you have so that you can map basically agents to ultimately tasks? Could you speak a little bit about an intuition, perhaps give an example of that?
Yeah, definitely. So basically the idea of encoding heterogeneity is that of splitting basically the robots' abilities at performing different tasks in features that the robots have and capabilities. So the features could be, for instance, like a specific type of wheel, like the Swedish wheels, or the wings, fixed wings, for instance. The capabilities could be the ability of fly or monitoring, for example. And so it is clear that you can fly with fixed wings or with the like propellers, as in a quadrotor setting. And so we want a mapping between features and capabilities that is flexible in this sense. So multiple features and multiple sets of features can serve the same capabilities. And that's where we used the bipartite hypergraph. An hypergraph is just a graph where the cardinality of each edge can be more than one. So basically we have multiple features that can serve a capability.
Okay, awesome. So the next question is related to this sort of relationship, but the question is about if you assume a binary relationship between capabilities and tasks, meaning if the task basically just either needs a capability or not, or is there a more nuanced relationship there?
Yeah, can I call you Sid, which is who is in this call, to answer this question?
Yeah, so that's a good question. So in the framework that we've presented in the paper, we do have a binary relation between the capabilities and the tasks, but we have sort of an extended weights formulation where we can sort of assign how much of a certain capability a task would need in order to be accomplished. And by assigning weights to the hyper edges that Gennaro was talking about, we can sort of propagate that all the way from the robot features.
Okay, oh, that's fantastic. Awesome. Thank you very much. Next up, we have optimal deployment of multiple passenger robots using sequential stochastic assignment. Do we have Chris Lee here?
Yep, I'm here.
Okay, awesome. Hi, Chris. Could you take a couple of sentences to summarize the work?
Sure. So we consider the case where we have a marsupial robot, which consists of a carrier robot, more robust, larger, carrying multiple passenger robots, which you can think about like a drone or multiple drones on this carrier robot. And as it's traveling through an unknown environment, the question becomes, when do you deploy these passenger robots? And so we formulate this problem as a stochastic sequential assignment problem, and that provides an optimal policy which informs us of when to deploy these passenger robots. That is only based on the remaining decision points. So if you consider like along the robot as it's traveling, there's only 40 decision points, let's say. And it also depends only on the distribution of the features of interest in the environment that we care about.
Okay, all right, thanks. So a question we have here is there a reason why the algorithm's performance seems to get better when you have more robots? But this is not the case for one of the baselines that you have, the CM baseline that you have, which tends to get worse. Could you speak about why you would expect that?
Sure. So the CM is the Cayley-Mosier algorithm, and it's a optimal stopping variant of something like the classic secretary problem, except in this case, the Cayley-Mosier focuses on the best expected value. And so the reason it doesn't perform better than the sequential stochastic assignment problem is because essentially the SSAP is an extension of the Cayley-Mosier, but to multiple deployments. And so the way we consider it, if you have 30 decision points and 3 robots to deploy, the Cayley-Mosier can only be partitioned. And so you can do every 10 decision points. You can apply that Cayley-Mosier algorithm to every 10 decision points. However, it only has local information of the distribution within those 10 decision points. The sequential stochastic assignment problem considers the distribution of the entire 30 decision points. And so it's more of a global maximum versus the local maximums. Yep.
Okay, all right, thanks. So the next question is about the reward. So there is a formulation in your paper which lets you sort of multiply 2 quantities, one related to whether or not you have this passenger robot, and then you have some dummy robots for which you assign 0. And then it's multiplied by this sort of reward for each location or candidate location that you have. I think it's denoted by X sub I in your work. Could you speak about how that reward is specified or computed and what's the intuition behind that?
Right. And so we test this algorithm by manually randomly placing quote unquote features of interest in the environment. These are just points that if the robot with a given radius drives through the environment, how many of these features it picks up. And that's kind of the reward itself. So let's say we find 3 features, and these features are meant to represent ideal locations for, in our case, drone deployments. So if you consider the carrier robot traveling through the environment, a good location for a drone would be ledges or overhead shafts or underground environments that ground robot can't travel to, but the drone is actually more capable of traveling to. So that's what these points are supposed to represent.
Okay, and just a quick follow-up. Do you assume you have this information a priori before you start sending out or deploying these robots?
Great question. Yes. And so right now in our initial work, we do assume, but future work, we're looking at either semantic labeling or other ways to tie these features of interest to better represent exploration potential for the drones.
Okay. Yeah. Awesome. Thank you very much.
Thanks.
All right. Next up, we have decentralized multi-robot task allocation with time window and ordering constraints. Do we have Elena on the line?
Yes, I'm here. Hello.
Hi. Hi, Elena. Could you summarize your work, please?
Yes, so pretty much our work is on multi-robot task allocation with time windows and ordering constraints, as you said. And so we are forming a team of robots like to collaborate on the tasks. So pretty much we're not only forming a team of robots that solving the task that, somewhere in a space in the map, but also they're considering the previous task that needed to be completed before the task can be assigned, as well as the time window where that task has to be scheduled. So for instance, if we have schedule, so the task has to be completed between 2 p.m. and 5 p.m. So, and certain task has to be done before that. We have, so pretty much we have a team of robots that are able to do it.
Okay, thanks. So the first question is related to the decentralized aspect of your work. So the question is actually twofold. One is, where is the precedence graph stored? And the other one is there one of the robots which is responsible for running the maximum algorithm?
So pretty much how we set it up right now, we don't have one particular robot responsible for that. We're more like computing it in the computer, and each robot is responsible to create its own schedule, like based on the results that we are getting. And so that precedence graph is stored also in the like in the main computer that calculates the max sum and everything, and just gives the information to the robots. And so basically then they are corresponding from there.
Okay, so there's a central computer that computes the algorithm and passes on the information. Okay.
Yeah, exactly. I mean, for the future work, we are planning to do something like that, like, that where we have different robots, like maybe not one particular robot, but different robots that have communication and ability to compute that. But what we have right now, it's more centralized.
Okay, so the next question here is, do you assume that the task execution time decreases just inversely with the number of robots in the coalition? So for example, for any task that you take, do you just boundlessly, do you assume that as you put on more and more robots, the task is just going to be computed faster?
So what we do, we are dividing the task duration time on the amount of robots. So basically, if we have 5 minutes task duration time, so each robot will perform 2.5 minutes of a task. So pretty much we are assigning it in the way that, yes, it depends on how many robots we have in the coalition, that will reduce the task. So this way we can, even though, we have certain constraints there, if, the robot has those 2.5 minutes, it's able to do it. Yes.
Okay. Yeah, just a quick follow-up on that to wrap things up. So do you think it would be possible to sort of put a bound on this number? For example, what I'm imagining is after a certain point, having too many robots is probably a very cumbersome task. We could make the assumption, of course, that makes the problem easier, but then in the deployment, it's not going to be very practical.
Yeah, so we do have it actually. We have it in our code that we have a function that limits the collaboration on the task. So basically, yes, that's based on the number that we get, and we are limited. Right. So yeah, we don't go for, too many robots for one task.
Sure, that makes sense. Awesome, thank you very much. I think that covers all the spotlight papers that we wanted to discuss here. Before we move on to the invited speaker panel, I suggest we take just a very brief 2-minute break. If you want to stretch your legs, get some water, that kind of stuff. Please feel free to do that, and then we will be right back in 2 minutes. You can stay on the call. We will just be right back in 2 minutes to begin the invited speakers panel. Thank you very much. Okay. We'll just give it a couple of seconds or for the speakers to join the call. Okay. All right. I think we have everyone. All right. Thank you very much. So let's just get started. So first of all, I would like to take a second to thank all the invited speakers for graciously accepting our invitation and preparing really insightful and exciting talks. I hope everyone got a chance to watch them. They'll continue to be hosted on YouTube, so you can watch them even at a later time after we have this discussion. So we have 6 great speakers here. So I will just go over briefly the format of how we are planning to go through this panel session. We are hoping this panel session can be a little more interactive than the spotlight presentation, because we had a lot of papers to go through last time. Here, I invite the speakers to interrupt as if they have any questions as they come up. So we will start with going through the speakers sequentially, and we will address some of the questions that we have gotten from the participants. And as we do that, other speakers feel free to jump in as you please, and we can make this more of a discussion. And then once we go through the questions for each of the speakers, then we will have a brief session at the end where there are some general questions that the participants have for you and would love to hear your take on. Okay, all right, I'll stop sharing my screen. Great. So we first have John Howe. Before we dive into the questions, could you maybe take some time briefly talking about your work that's been presented in the talk, and then that will be context for the questions.
Sure. Good morning, everybody. So I'm John Howe at MIT, and the work I talked about in the presentation covered 2 of the recent bodies of research we've been looking at. One has to do with distributed, scalable sort of formation flying vehicles. It's thinking specifically about an architecture and a software pipeline, as we sort of have put it online. That's looking at how we address both the sensing parts of the problem using a distributed VIO software, how we'd look at the formation control from the perspective of task assignment, collision avoidance, and also just the sharing of information between the vehicles themselves. And one of the specific things has to do with the assumptions about the frames used by the vehicles and whether or not they have aligned those or not. And that leads to, if they're not aligned, and by not aligning them, we don't have to exchange that information, we then end up in a situation where there's an error that has to be accounted for in the tasking itself. And we show through the algorithms how that error can be corrected for and then handled. There is a centralized component to the algorithm which does the calculation of the gains, but that's basically a determination of what the formation would look like from the perspective of each of the UAVs. The online component, though, is entirely decentralized. The second piece has to do specifically with resource-aware tasking for the vehicles themselves. We look at it in the context of cooperative SLAM. So there's a question of loop closure. That's a very computationally and communication-intensive problem. And so we want to take into account those resources when we actually decide what effectively becomes a communication policy, which is what should be exchanged and with whom. And so the vehicles in that particular context of that problem, the vehicles come up with a communication policy in real time that's solved to determine how that information will be exchanged. And so it's sort of, it's very specific, but it gets into the details of a very key problem in the area of heterogeneous UAV work.
All right, thank you so much. So we have a few questions here. We can go through that. I also wanted to mention that participants feel free to unmute and ask a question if that comes up for you as we go through the discussion, and we can make it as much interactive as we possibly can, given that this is a Zoom call. So the first question we have here is, what do you see as the challenges that are involved in extending the formation control approaches you talk about to teams that have heterogeneous robots? For example, if certain positions in the formation could only be taken by certain robots, how easy or challenging is it to incorporate these sort of constraints?
Yeah, that's certainly a key question. I mean, you'll see in the way that the tasking is done, there are sort of assumptions made about the team being homogeneous in the sense that we are able to just decide within the teams how to do the assignment and essentially reallocate the positions in the formation. If you ended up in a situation where the positions of the formation themselves become reliant on the capabilities of the vehicles, then you have to start including those constraints. So you sort of move away from the very simple form of the auction that we had into a more complicated version that we had looked at in the past. So this ends up being something that we call CBAA. Sharon recently mentioned CBBA. The difference between the two has to do with bundling and things like that. We don't need necessarily to think about lots of tasks here, but what we do need to account for is the constraints of which vehicles go and where. So one of the things you could do is essentially run multiple auctions in parallel, one which is for a subset of the tasks. And so the vehicles themselves know just to bid on the tasks that they're actually capable of. It gets more complicated if you add in sort of variations on capabilities and so on. But there are versions of these tasking problems that we've looked at in the past that have essentially problems of the type where each of the vehicles themselves have a certain set of characteristics, and each of the tasks have sort of a mapping of those characteristics that is necessary, and you end up in situations where you have to account for those constraints. So the version we have now is simplistic and doesn't handle that. On the other hand, if you could include that, it just would get to be a more complicated version of the tasking.
Okay, thanks. So the next question we have here is, would it be possible to respond to changes or reductions in the budgets? I'm assuming this has to do with the second part of your talk, that you consider budgets.
Yeah, well, the budget, so the policy is done as a real-time calculation. So I think somewhere in one of the slides was sort of a statement that there's sort of an understanding of what the network connectivity would look like and and so we're exchanging the metadata, which then gives us a sense of what it is that we think we would like to exchange. The calculation then for the actual communication policy is done within an understanding of what those budgets actually currently are. So if you had a change in those numbers in real time because, for instance, you wanted to start spending more communication budget or more computation budget, then you would just, as you're rerunning that policy, you would basically account for the changes in those numbers as you go along. So in that sense, it's a lot like NPC. I mean, it's a real-time optimization done subject to the constraints that exist at that time.
Okay, awesome. Another question here is, could you speak about sort of the similarities and differences between the proposed approach and consensus-based approaches?
Well, I mean, the first approach is a consensus approach. I mean, in the sense that they are doing consensus on tasks. One of the themes that we've been looking at through our body of research has been the assumptions about what you're doing consensus on. And so typically we think about it in the context of doing consensus on knowledge, so the situational awareness. And so the whole discussion about frame alignment and whether or not you're aligning the frames gets into the issue of, are you doing consensus on that information versus doing consensus on the task. And so then there's sort of an agreement on who should be doing what. The typical challenge with just doing consensus on information is that then you have to run a tasking algorithm on top. And then the premise is that the output of that tasking algorithm is all the agents are in agreement. The difficulty is you don't know that. And so you end up in what is sort of commonly known as implicit coordination. Whereas if the assumption is if we all agree on the information and we run a deterministic algorithm based on the same information, we will come to the same answer. the challenge in real life, as many have found out before, is that we don't have the same information, and it's explicit here because the vehicles are measuring different things. And they're not running a deterministic algorithm necessarily when you're actually running a large-scale constraint program for doing the tasking. So when those two things get violated, you can have a situation where the vehicles now are actually coming to it, they're not agreeing, and then they would actually think that they're being assigned to a different task or location within the formation, and then they sort of fly there and then realize, hey, oh, there's a problem because we're both going to the same place. So in the absence of that of knowing that implicit coordination is necessarily going to converge to the right answer, you then have to do some type of a check to make sure that everything's okay. Now you can do like a repair check where you simply are just saying, hey, let's check and make sure everything's okay and we're all in agreement, and then do like a repair in the sense of, oh, if there's a disagreement, we'll find a solution to that. The problem is that that repair can itself snowball into everything having to be reassigned, and that there's no sense necessarily of a small reparative assignment problem, because if you have a conflict, that conflict and resolution of the conflict can snowball into lots of other changes. So this is why we've focused more recently on just getting agreement on the task that's been done. And the whole the whole points of sort of a technique like CBAA and CBBA is that they really don't make any assumptions about knowledge, and the knowledges can be quite different, but the agents, based on whatever knowledge they have, do a bidding for whatever task they want. The tasking operation occurs, and the result of that then is an agreement on who is actually doing what. Agents may decide to do things for the wrong reasons, but they're all in agreement for doing the right thing. The result is a performance reduction because of the lack of consistent knowledge. On the other hand, you have agreement. And if you want tasking agreement, then this is sort of the way to go. So again, there's many ways to sort of achieve that. And so I think when people think about consensus, it's typically on the situational awareness as opposed to on the tasking. I think what I'm trying to argue for is you really need to be doing both aspects of that to be confident that the end result will actually be without conflicts in the tasks themselves. And so if you have to do both, then why not just do the second one? And if you have communication capability margins left, then you could spend that on improving the consistency in the situational awareness, which will improve the performance of the system. But if you don't, then just focus on doing the consensus on the task.
Okay, awesome. So before we move on to the next speaker, in the interest of time, if there are any pressing questions from the participants, feel free to ask them. If not, I think Ragesh can take over.
Yeah, thanks, Harish. So our next speaker is Dimitri Penal, and she has, Dimitri, can you just briefly describe your work that you've talked in the talk, just to have the context being clear, and then we'll go to the questions of it.
Yeah, thank you. So hello, everyone. I'm Dimitra Panago with the University of Michigan. So in this talk, I focused on 3 topics currently investigated within my group, and I tried to show some of their overlapping and interconnections. So the first part of the talk was related to a control design in the presence of adversarial agents, where the focus was the adversarial agents are viewed as agents that share wrong or malicious or faulty information with their neighbors. And I highlighted some of our results on the communication structures, the control algorithms, and the information filtering algorithms that can guarantee resilient consensus and consensus-based controllers for the team of the non-adversarial or the good agents. In the second part of the talk, I focused more on problems that have to do with spatiotemporal control synthesis. So we are interested in problems where one agent, or currently we're extending this work to multi-agent systems too, have to accomplish objectives that have both state constraints, for example, safety, and temporal constraints, for example, timed reachability or timed convergence to desired sets or destinations. and how we can compute controllers for this type of problems using optimization techniques. And in the third part, I focused more on planning techniques against, again, adversarial agents, but where the adversarial model has mostly have to do now with a physical interaction between the agents. So we are interested in problems where there might be two teams of robots, and one of them might want to reach some area that is protected by the other team. And the question is how the, let's call it the blue team, can either hurt or intercept the red team so that it does not approach this protected area. And we're interested in understanding, like starting from simple adversarial models, for example, knowledge of some upper bound on the velocities or the accelerations of the bad agents, how we can keep building more sophisticated models of understanding the adversarial behavior, and then replanning in order to achieve the herding or the interception strategy by the blue agents, the defenders. So this is ongoing work, and I gave some of our preliminary results in these topics.
So thank you, Dimitri, for that enlightening summary. So the first question that we had is actually has three parts. Basically, the question is about how useful is the robust notion in practice, and what are the other promising directions that we can use with the WMSR filter other than the RSS one, and in your opinion, what are the advantages and limitations of the WMSR approach?
Yeah, so yeah, that's a very good question. So I mean, definitely the R robustness and RS robustness and this framework has been developed, and it does give us fundamental characterizations for essentially maintaining the connectivity of the network under this class of adversarial agents. When it comes to practical applications, one can think of the question of how can you first of all know the robustness and RS robustness of an arbitrary graph. So the combinatorial nature of the definition makes the problem at least MP hard in order to know, to have an algorithm that in an efficient manner gives you the robustness and the RS robustness of your graph, of your communication graph. So that's one aspect. The other aspect could be, when it comes to challenges, could be, let's say that maybe you have a class of graph for which it's a robustness, then how can you maintain it in a practical application where you might have disruptions in terms of the connectivity, in terms of the communications between your robots, limitations in terms of like how far the robots can be in order to establish efficient links, reliable links, and so on. So I think that there are approaches where there's ongoing work on how you can design teams that maintain formations in a way that maintain essentially the R robustness and the RS robustness of given graphs. So that's one way of going around the problem, which it's an open challenge on its own, because then that means that leads also the question of how you can maintain their robustness with limited information, like in a distributed way, when essentially this is a property that requires global knowledge of your network. So then the question would be maybe how you can approximately have some notion of our robustness locally, and how you can, if it is broken for a while, then how you can maximize the chances of reconnecting your robots. So, and how this is related to the overall planning that you are doing for your formation among the obstacles and so on.
So this is one way of research with all its challenges. The other way that I could see as a interesting direction, which is also related to the second part of the question, how you can go maybe away from the WMSR algorithm. So, so the WMSR helps with essentially the principle of filtering out the outliers with respect to your own current state. And it has its pros and cons. It's pros in the sense that you can do a mathematical convergence analysis and guarantee that eventually you will reach consensus with your good agents. But the principle on its own might be limiting in several applications. So why just filtering the outliers with respect to your own state is the right way to go? Is a question that I guess the answer depends on the application. So there might be applications where you might want to use additional information, prior models about what constitutes an adversary or adversarial or non-nominal behavior. So I could see how the WMSR principle can be augmented with other detection strategies at the same time, so that so that you can have some additional way of detecting the adversaries, and then once you know which agents constitute adversaries, then you directly kill communications with them. So essentially that could be an additional layer of maintaining resilience in your system. Now, other approaches again that go beyond the WMSR. So, for example, the MSRPA algorithm, for which I talked in my talk, is essentially more of a resilient broadcast algorithm where the agents want to receive information from the leaders. From some agents that are viewed as the leaders in the network. And so the question is how this information can be broadcast, can be propagated resiliently in the network, across the network, so that all the followers are able to reconstruct the correct information. And with this information, be able to take actions and make decisions and take actions for themselves. So this is, again, something that relies on the notion of robustness and RS robustness. You want to have an robust graph or RS robust graph in order to guarantee that eventually all the agents will be able to reconstruct the actual, the nominal value of the information and not the corrupted. They are not fooled by the corrupted value that some leaders might want to send. But at the same time, it does rely on this structure, but it is not WMSR in the sense that it doesn't kill out the outliers. So it's a different way of propagating information throughout the network.
Okay, thank you for that answer. So the next question is, like, how do you compare your approach for the resilient constructing from that you can actually model the same problem from a robust control perspective?
Yeah.
So like modeling like a disturbance rejection. So like what's the additional advantage that you have in your kind of formulation?
Yeah, so I think conceptually there are many similarities in how these problems can be formulated. So I think that one of the advantages of considering this type of adversarial Byzantine models is for the adversaries is that essentially you do not have to consider any upper bounds. So essentially the adversarial model can incorporate bounded disturbances or unbounded disturbances, and what the good agents, or essentially what the good agents are supposed to do is kill out, crop out the outliers. So essentially so they can counteract disturbances that are not of known a priori bounds. So what we do is we put a bound on the number of the adversaries, not on the signals that they are communicating to the network. I think that that's the fundamental difference. But once we see there's a problem of putting a bound on the number of adversaries, you can think of it as a robustness problem in the sense that you're robust with respect to F local or F total adversaries in your network.
The final question that's posted out here in your fixed time spatial temporal control work. So how do you guarantee that the safety barrier certificate is actually working? I mean, what's the intuition behind it? Because you were using Slack variables to actually introduce the problem.
So the underlying assumption there, and maybe I didn't make it clear when I was stating the problem, is that Nagumo's theorem holds on the boundary of the safe set. So essentially, there is a solution for this safe set that we want to render controlled invariant. So that's a big assumption, of course, because that means that every safe set that you consider is a viability domain for your system. And then essentially what the Slack variables does is to give you, so we solve the problem with priority on safety. So we can find a safe controller under the assumptions that I stated. And the Slack variables help guarantee that if the time constraint can be also met, then the QP can find this solution that satisfies both safety and the convergence within some time, within a given time, to desired destination within the safe set. If this concurrent satisfaction of those constraints cannot be met, then the QP is going to find a trajectory that is going to converge to the destination without exiting the safe set, but within a time that does not mean the prescribed specific time specification that was given by the user, but is rather a time that depends on the initial conditions and on the parameters of the system, the control inputs and so on. So that's the intuition behind those results.
Okay, thank you, Dimitri. Harish, you can actually go for the next speaker.
Okay. All right, thank you, Rakesh. Next up, we have Gal Kaminka. Thank you again, Gal, for a very exciting talk. I see that you already responded to several questions on the Google Doc, so we will go over a couple of them here. So before we do that, do you want to take a moment to summarize the work that you talked about?
Yes, thank you very much for this opportunity again. So very happy to participate in this panel. So essentially my talk was divided into two parts. Both of them were reporting on current research themes that are going on, and research efforts that are going on in my lab, both dealing with swarms. And in both of them, there's a significant role for heterogeneous swarms in particular. The first part talked about robots, the swarm robots of the type that we usually see in these talks, about a fist size and moving about and pushing things, or moving about and navigating. And we've had a lot of success in using reinforcement learning with intrinsic rewards, which are interesting because these are rewards which only require the robots themselves to know about their times of execution. So they're very well adjusted and very appropriate for learning in real robots. And most of the talk really focused on the latest set of results that we have, which is actually moving beyond the success in experiments and understanding why these things works, because reinforcement learning in general, Q-learning in general, does not in general converge in multi-robot settings. But we have a specific explanation for why these things actually converge and are very stable. And in some sense, the key insight that we gain from this is that heterogeneous swarms can be rational, in the sense that the entire swarm is actually converging to a Nash equilibrium. The second part of the talk focused on nanobots, which are actually robots that are molecular size, that is nanometers, a few nanometers to a few hundred nanometers. These days, it's very fashionable to talk about viruses. So if you want a point of comparison, the robots that we work with are actually smaller than the COVID-19 virus. And these are robots that are very simple. They can open and close, and that's it. So they can, in fact, only do a single if-then statement. And heterogeneity is, in fact, extremely needed, because otherwise you can't do actually anything very complex. And just to show that, in fact, we can do something complex, what we've done is carry out Asimov's 3 laws of robotics in molecular robots by introducing a swarm that was actually able to carry out a task, then turn itself off if it was causing harm. And well, it's in the talk, but the third robot is actually maintaining the balance between them to make sure that this actually works. So this was in a very short summary, in a sense, of what I presented. And yes, I took the I treat the panel seriously. So you guys wrote questions, so I wrote answers.
Thank you. We really appreciate that. Thanks for the detailed answers with some references too. So I'm going to play favorites a little bit, and I'm going to ask a question slightly out of the order. There is an interesting thing that you show when you have this heterogeneity, and you show that having this heterogeneous strategies is very beneficial. There's a graph that you show that sort of proves this. And one of the things that I noticed was that at the two ends of the graph, the performances of the individual strategies themselves, if 100% of the robots were following strategy A versus strategy B, one strategy seemed to be better than the other. Even in those cases, it is very interesting that you see combining, let's call it optimal versus suboptimal strategy still seems to be the best you can do, as opposed to having every robot do what is the best strategy. Could you speak a little bit about that?
Yes, so the graph you're referring to indeed shows on the x-axis, it measures a homogeneous swarm on one end and homogeneous swarm on the other hand, and then all the combinations in between. Right. And what it shows is that if we fixed ourselves to only homogeneous swarms, then you get, the points roughly about here. But if we allow the learning to take place, which is what we talked about, then you actually get some points which are higher up, somewhere in the middle. So by introducing or allowing the swarm to become heterogeneous, you actually do get an optimal result. Now, we've actually had also experiments in which the homogeneous swarms on one end or the other were actually the best. So the point is not, and in fact, I think this is, it might have been, I came out so forcefully in favor of heterogeneous swarms that it might actually have taken the message over there. So I want to emphasize, it's not that I'm claiming that heterogeneous swarms are always better. In the nanobots, it's the only way to go. So you have to have heterogeneous swarms are there. You can't actually do anything. But in this type of robot, they're sort of normal looking swarm robots that we see in talks everywhere. The claim is not that the homogeneous swarms are always worse. The claim is that homogeneous swarms can often be worse. And the heterogeneity and the game is in fact finding the point in between where it's going to be good. Now this is where it gets hard because of course, we did lots of tests which is randomized swarms, just from randomized mixtures. So and they fail, right? So randomly assigning trying to heterogeneous mixtures, it just doesn't work. You really have to get to this. The point of the learning was that in those experiments where homogeneity was actually the best, the learning converged to that. So the robots were not insisting on heterogeneity. They were allowing themselves to become heterogeneous for the swarm. And I think that is that was an interesting, a real revelation for us because we really did not know which side we're going to be. What we found out, and this is in earlier work, which I'm pointing to from the paper, from the presentation, and I'm perfectly happy to send to give more detailed pointers. But in earlier work, we know that homogeneous swarms are just not good. I'll put it differently. There is no one single method that everybody can use and will always work well. So even in cases where homogeneous swarm is the best, with a slight change in the settings, in the density around the swarm robots, in the area that they have to cover and so forth, then suddenly that homogeneous method, which worked so well before, is just no longer working well. Okay, so this is really was an insight some years ago that led to all of this work, trying to understand why, how the learning works and why.
Okay, all right, awesome, thank you. So the next question, if you can answer, is how can we extend the ideas presented in the nanorobots part, because you had this 3 types of cool robots that try to mimic Asimov's laws. Could you think of more complex ways in which we could have these sort of very simple robots that can do very simple tasks? Could we break them? So could we sort of take them together and have them perform more complex tasks? Is it just a matter of having more types of robots, like you had, for example, in this case, 3 robots, in order to create iteratively more and more complex behaviors?
Yeah, so first of all, let me assure you, I'm talking to roboticists, so take me. So I'm talking about the 3 laws of robotics, and I emphasize in the talk, this is a philosophical device. So for those of you who are participants in this and are watching me and they're saying, who is this nuts who thinks Asimov's laws are serious? It's not that I think they're serious, I think they're interesting. They're interesting because philosophically they raise interesting discussion about whether a swarm can do something complex, nothing more than that. Now, the real issue is it looks very, when you cast it as nanobots and heterogeneous swarms, then it becomes something almost like, science fiction-y, and it sounds very complex and stuff. But actually, think about it a completely different way. So if I went to you and I talked to you about building this extremely complex device that's made only of transistors and resistors and other silicon-based components, you would say, oh my God, but we have VHDL, we have hardware programming languages. At the higher level, of course, we have Python translated into something else. It goes all the way down to the CPU, which itself has been designed also with computer software. And finally, there's hardware description languages and compilations, which actually now burn the whole thing and create a chip. This is the kind of mode of thinking that I think is going to be needed for this type of task. So the Asimov example was really just an example. The paper that actually describes the mechanism by which you could design this thing is a different paper. And it talks, it's from each guy, and I pointed to in the Google Docs right now. I'm also pointing to from the presentation. But it's a paper that was describing a compiler that would actually take a description of the task to be done and would find options for how to combine different kind of nanobots so that they actually carry out the program, right? What you want. And it sounds as if at the beginning as if something, something very, very fancy in terms of conceptually, but actually conceptually, it's very simple for engineers to understand. It's when I talk to biologists is that they think I'm crazy, but biologists really don't understand what a compiler is. By the way, the whole paper with Asimov started because my biology partner actually thought Asimov's laws were, our holy grail. So I had to take him off that, wean him slowly off the philosophy. So the real goal here, I think the automation and the compilation is the way to go. We can continue to invest in more complex swarms for this type, which would be manually built. And I think for the next foreseeable future, we would necessarily have to do this on occasion because we have to find the range of possibilities for what does the compiler have to play with, right? These are components that we don't understand. It's not like a resistor or or a transistor, right? We don't understand how these things actually navigate, and in some sense, or in many senses, these are much more complex because nanobots, they're themselves chemical or biochemical devices. They have half-lives. They don't always work. So it's like working with really bad hardware, okay? And yet, I think the way to solve this is still to treat them as components which have to be put together. Once you think about that way, then suddenly all of us engineers are saying, okay, hold on. You want a three-prong end, but you're only given, a two-prong end. That's not a problem. We'll just chain them together, right? We'll do this, and that's how we know how to do this. This is very simple combination of logic functions. So again, when you talk to biology, they don't understand it at all, and they begin by explaining that you're wrong. Believe you me, after 20 minutes of explanation, they say, okay, well, there's something to the idea, and now the discussion can move forward, and they usually move forward to understanding why it doesn't actually work like an end. And that's the interesting discussion we should be taking with them. So, because it's not as robust and it's not as understood as the logic gates that we have today, but it is something that can be mapped and that we can have automation take care of, okay? So this is I think the direction to take with this.
Okay, awesome. Thank you very much. So in the interest of time, I will not ask the other question, but Gal has kindly answered the question on Google Docs, so we can do that. And I'm sure some of these will come back up when we open questions for the general panel. Thank you so much, Gal.
Thank you very much.
All right, Ragesh, do you want to take over?
Yep. Thanks, Harish. So next speaker is Cradle Solvay from Stanford. So Cradle, can you just give a brief summary of your work before we take on with your questions?
Hey everyone, of course. Thanks for having me here. So the talk that I presented shows my most recent work on the intersection between multi-robot systems and the operation of smart mobility systems. In particular, we're exploring ways of how we can use multi-robot systems in order to improve our current transportation systems. One particular example that I'm showing in the presentation is the operation and control of autonomous mobility on demand system, where the goal is to satisfy the demand of passengers willing to travel in a large city using, using autonomous vehicles, which provide services which are very similar to what we currently have with Uber and Lyft. And for this specific problem, we present an efficient algorithmic approach that is also congestion aware, meaning that it is aware of the congestion that it itself introduces. And by that, it strives to minimize the congestions. The second work that I presented is concerned with improving our current services of package delivery. And the way that we propose to do that is using a large fleet of drones. The problem with drones, however, is that their flight range is very limited. So the way that we are proposing to overcome this problem is to allow drones to land on top of public transit vehicles. And by that, they can hop between different vehicles and ride on them such that they get closer to their final destinations. And by that, they conserve their limited battery energy. So throughout this talk, I also highlighted a few situations where task allocation is a key component in those problems. And I also highlighted a few important social aspects that should be addressed when designing such systems.
Okay, thank you, Kirill. So in the interest of time, I'll just pick some of my favorites and from the questions posted. So can you speak a little bit about how the heterogeneous task assignment problem can be decomposed into this homogeneous problems, and what assumptions do you make in this decomposition, which is likely part of your talk?
So I just want to give a bit of context for the audience.
Yeah,
this was another work that I also briefly mentioned in the presentation, whose motivation is the study or data gathering on Mars and this is a joint work with our collaborators in JPL. So there we present an efficient approach for a specific instance of the heterogeneous task allocation problem, where the goal is to collect as much reward as possible using several fleets of robots. And what we show in this work is that for the specific problem setting that we're exploring, it is possible actually to break the heterogeneous problem into multiple, or a small number actually, of homogeneous problems, where every homogeneous problem can be solved efficiently. And if you go through the math, which is not that complex in the paper itself, you can see that once we break the problem into homogeneous problems, we can also convert the individual homogeneous solutions into one heterogeneous solution while still maintaining a good approximation factor with respect to the optimal heterogeneous problem. So I hope that this answers your question, although I didn't really get into the details, but I think due to the time constraints, I will just refer you to the paper.
So another question is, what are some of the challenges that from a technology and social perspective that you foresee in the system approaches that combine robotics with in city infrastructure? It's more of a philosophical question, but yeah.
Mm-hmm. So the challenges are numerous, and there are researchers and policymakers that are working on those issues from many different perspectives. For me, the biggest challenge would be to try and capture as much or model as accurately as possible the real world when we're designing our algorithms, in order to make sure that our algorithms would actually perform as they are supposed to, and they would lead to good solutions and would help us to overcome many of the challenges we're currently facing in present transportation systems. For me, the most important thing is to make sure that we're not only able to overcome or fix different social disparities in our society that are currently related to transportation system, but also make sure that we're not causing new issues. So for that, we really need to understand the human component, the users of our system. How would they behave and how would they interact with our systems?
Okay, thank you, Kirill. We move on to the next speaker in the interest of time. So Harish, can you just introduce me?
Okay, yeah, thanks. Next up, we have Amanda Perog from Cambridge. Thank you once again, Amanda, for your excellent talk. We have a few questions here, but I will give you a moment to talk a little bit about your work so we can contextualize the questions.
Thanks, Harish. Thanks. Thanks again for organizing this workshop. So hi, everyone. I'm Amanda Perog. I'm at the University of Cambridge. And I talked about two things in my talk. So the first thing I talked about was about using graph neural networks to enable robots to learn what to communicate to coordinate. So basically the question that we're trying to address here is in very hard coordination or even planning problems, what is it that robots have to communicate in order to get as close as possible to centralized to the centralized optimal counterpart algorithms. So the specific case study that we actually consider is the problem of multi-agent path planning, and there are actually two reasons for this. The first reason we were really excited about looking at that problem is because it's an NP-hard problem, so it's a difficult problem to solve, independent of which optimization objective you're trying to optimize, so either flow time or make span. And the other reason that we decided it's a good place to start is because we know that optimal solvers exist for this problem. So whatever learning method we're going to be using, we can benchmark it very cleanly with respect to these optimal solvers. And so what we basically showed is that we can actually perform extremely strongly with our GNNs. So we have success rates up in the very, very high 90s for a very large set of case studies that we, so map case studies that we considered to solve, so 98, 99% success. And our flow time increases were incredibly low with respect to these optimal baseline benchmarks. And the other thing that was really nice is that we were able to generalize very broadly to unseen instances. So for example, if we trained a system on 10 robots, we could then take the very same learned parameters that we got from this training process, deploy those learned networks onto systems of many more robots, say 60 robots, and the results were still very strong. So we hardly had any decrease in performance. And so this is really where we think this kind of method comes in extremely handy, because we're suddenly able to, with one, albeit expensive, offline training process, we then can solve many different online instances, irrespective of N, so the number of robots. And so the second thing I talked about in my talk was how to use redundancy in multi-robot systems, and why is redundancy interesting? And so clearly in our case, in that particular piece of research that I presented, we're looking at a large team of robots that have to reach goals, so reach targets, where at those target positions, there's a task that needs to get done as quickly as possible. So we're basically trying to optimize the time it takes for these robots to get to their target positions. And employing redundancy turns out to be something very interesting to do when you don't know exactly how long it'll take any robot to reach these target positions. So the interesting point or the interesting thing about trying to solve this problem is that it's hard, again. So we're trying to solve a set cover problem because we have redundancy in the system. And so we're trying to find out what robot coalitions are we going to create in order to assign to these tasks so that we can actually get the best or reap the most out of these redundant assignments. And basically, I point out that there are two interesting things about the way we can actually solve this problem. First is this insight that in the case where we're actually traveling to our targets, we're considering, with redundancy, we're considering this thing, which I'm calling first come, first to serve, right? So it's the first robot that actually reaches the target that is the one that's going to do something about the task there. So that idea is crucial to our mathematical formulation. And the other idea that is crucial to making this problem solvable for us is that we can show that our optimization objectives are supermodular, where supermodular is just the inverse of submodular, since in this particular case here, we're minimizing the optimization objective. And that basically allows us to solve the problem with a greedy algorithm. And I show that we can actually do really well. And I also show that redundancy is actually really helpful when travel times are uncertain. So that's kind of the pitch of my talk.
All right, thank you so much. That's great. So one of the first questions we have here is with respect to the GNN work. I think it's sort of related to explainability. The question goes, are there any interesting structures in the learned parameters, I think you call it A, that indicate when non-local communication is necessary or beneficial?
Yeah, that's a good question. And actually the answer, I mean, there are many, many different ways I could answer this question. So first of all, when we increase the hop count, it's important to note that we don't, so the local communication is still taking that into consideration in the formulation that we're using. So that's one thing. When we increase the hop count, we're also increasing the number of learnable parameters. So you'll have noted that if you read my paper, if you read our paper, the learnable parameters, these matrices or these tensors there's an index of care. So we're increasing the model complexity. So that makes answering this question also maybe not quite straightforward. But one of the interesting things that we have actually done, and this is kind of a bit of a conjecture, but we've started we actually posed ourselves the exact same question. And we tried to look at this by using an additional mechanism. So for those of you who are familiar with attention mechanisms, it's a way of computing in specific scenarios where you have graphs, what incoming edges, for example, are transporting or bringing you more important information with respect to other edges. And we actually implemented some of these attention mechanisms, and some early empirical results actually do indicate that nearby robots are very important to this whole process. However, we're taking this with a pretty large grain of salt, because there's a number of issues or kind of points that we have to consider in this whole system. And the most important one is that we're actually currently modeling the whole system as a sequential decision-making process, which means we're not actually solving a planning problem, which normally you would be doing if you tried to solve the problem optimally. And because we're solving it in this sequential decision-making way, we're actually treating the problem as a reactive problem, and hence the importance of nearby robots. So this is all kind of we're kind of in an echo chamber, if you know what I mean. So if we would then try and more formally increase our problem formulation and try to expand our system architecture to more accurately represent that it is indeed a planning problem, maybe the impact or importance of local communication would be decreased.
Okay, there's another question that's pretty much a follow-up. So you mentioned how you turned this into a sequential decision-making process.
Yes.
Like in many other robotics applications, whenever you have sequential decision-making problems, sometimes your error starts accumulating and you integrate it over time. A mistake, let's say, you make in the first step might have consequences down the road. Do you experience something similar taking place in this particular set of problems?
Yeah, that's a good question. So I guess the first thing here is that it's in planning problems such as the one that we're considering right now. I think it's pretty difficult to come up with a way of really quantifying error as a function of time, because your performance is determined by what happens when all robots have finally reached their goals. So flow time or make span. So that I think is the first challenge here. And also I think so it is clear, I mean, one thing that we could track is as soon as any single robot deviates from the optimal path, we could potentially consider that as a loss in performance, but it's not clear that it necessarily needs to accumulate. So there might be multiple solutions, and it's not inconceivable that this loss that was incurred at that time step is not redeemable at some point later down the road. And again, it's a convoluted question in the sense that it combines with a couple of other design decisions that we made. So not only are we considering our problem as a reactive problem, but also we're decentralizing our system. So we're only allowing the agents or the robots to consider their most immediate neighborhood, right? So in that sense, it's very so what we need to do in order to make justice to the planning problem is try to incorporate information beyond the local horizons, and then basically include that into the way that we're trying to evaluate the performance of the system.
Okay, thanks. So there are a few more questions, but I don't think we will have time for all of them. So I will ask one last one before we move on. So could you comment on which parts of the optimization problem that you design and the framework that you propose ends up incentivizing diverse solutions? In some part of your talk, you talk about how you generate diverse solutions and you compare it with a baseline algorithm, which tends to take the same path over and over again, but you tend to have diverse paths.
Yeah, so this is talking about the second piece of research that I talked about. And that's a really, really interesting question, actually. So maybe just to recap, so in that particular optimization problem, we're looking at costs where the costs are per robot, per task, and per path. So we have 3 indices that we're trying to basically optimize over. And this diversity, it emerges with respect to the index K, which is the path subindex. And basically what's happening is that, well, what the algorithm does is it basically is trying to, it evaluates the marginal decrease in cost that it would incur with respect to all possible or eligible assignments that it could make, and it will select that particular assignment that will increase that marginal decrease, that has the largest marginal decrease possible. And in this particular case, diversifying over K is what provides larger marginal decreases to the system. Okay. But why I think the question is so interesting is the fact that you've kind of pinpointed that we can maybe find more explicit ways of optimizing for diversity by including these spaces or that dimension as one of the indices or one of the dimensions that the algorithm has as an option to optimize over, right? So in this particular case, the greedy algorithm just found out, or it emerged from the selections that the greedy algorithm did, that diversifying over paths and not always choosing the same K was the right thing to do.
Okay, awesome. Thank you very much. I think there are a few more questions, but if you have a chance to address them on the Google Doc, we really appreciate that. Ragesh, do you want to address questions to the next speaker?
Yeah, thank you, Harish. So next we have Vaibhav Srivastava from Michigan State University. So Vaibhav, can you actually briefly summarize your talk? It was actually very interesting, a quite different talk from which bring a diversity from the biological perspective. And can you just give a little context to the audience before we can actually answer some of the questions?
Sure, thanks. Thanks for organizing this panel and inviting me. So what I talked about is how do we seek inspiration from biology, which inherently has all this heterogeneity and always leads to some sort of robust and flexible behavior. So to example from 2 specific systems, and this kind of phenomena is prevalent in other systems as well, but I focus primarily on honeybees and animals on the move. So these animals have heterogeneous group of agents which have different preferences, and there's always going to be conflict in these animals, but these animals need to move together because if they don't, there's a risk of predation and other kind of things. So we looked at the mechanisms that explain the collective behavior in these animals, and it turns out that the bifurcation phenomenon is something that that explains many of the behaviors that we've observed in these animals. So the animals kind of look at some sort of singular limit, and the bifurcation takes place at that limit. So we looked at how these bifurcations yield a flexible and robust behavior. And then we developed a model that is distributed. We can implement it on robotic systems and can embody all the beautiful and rich behavior that we see in animals. So we talked about this model and looked at what kind of different heterogeneities can be present in a system in that generalized model. What is the influence of those heterogeneities? And then how do we adaptively in a distributed way tune the parameters of these model to achieve the kind of behavior we want?
So, thanks, Vaibhav. So the first question that so there are a few questions, so I'll pick some of my favorites from it. So the first question I need to ask is, does the quality of information change during the decision-making process, such that it impacts the associated social effort? Sorry, the natural does the quality of information change the social effort?
Yes, it can. It can absolutely can. So one of the nice things that when we talk about, which I did not go into too much detail in the talk, but one of the nice things that when we organize the decision making using dynamic phenomenon such as bifurcations, there is some robustness that comes in naturally due to this perturbation. So there is something called hysteresis that happens in these bifurcations. So if you start reducing the quality of the information, there's a robustness to the decisions that you have made. So until a certain point, if you start reducing the quality, your decision is not going to change. And if you reduce it too much, then yes, your decision will change. So that robustness in your decisions comes out of that hysteresis phenomenon that is associated with those bifurcations.
So the next question is, your general model do you consider it has a lot of stochasticity and stuff. So did you consider modeling it as population density, like something like deriving a Fokker-Planck equation and deriving something, and then you can have some useful stuff from there?
Yeah, so that's a very interesting question. So yes, Fokker-Planck equation can give you a lot of insight. So right now, when you look at the deterministic model, all you can say about there is some sort of asymptotic behavior that happens. There's certain basin of attractions in which a particular kind of behavior will be exhibited. And with respect to Fokker-Planck equation, when you analyze that, what you can say is something about more about the finite time performance. What you can talk about is how different trade-offs are exhibited. For example, how speed versus accuracy trade-off in collective decision making is exhibited. So we have done some of those works. When you consider a linearized stochastic model of the generalized form, then we have been able to apply Fokker-Planck equation on that and characterize some of the speed accuracy trade-off and what is the finite time influence of heterogeneities on the systems.
Okay, so thank you, Vaibhav. In the interest of time, we'll have to wrap it up. And so there's, if you have time, please feel free to actually answer some of the questions out there in the Google Docs, and we'll come to that later on. So
Sure,
thank you for joining us.
Thank you.
All right, thank you to all the speakers. So I think now it's time for us to move on to the general panel discussion. So we have a few questions that are directed at the panel in general. So I invite the speakers to just feel free to jump in if a question is of particular interest to you, and we would love to hear from your opinions. And I also, again, encourage the participants to ask any questions that come up for them based on the discussions we have had so far. You can use the chat, you can unmute and speak here, or you can use the raise hand feature, I suppose, on the Zoom, whatever you feel comfortable with. All right, I suppose we can get started with this question. This is more of a generic question, and we're very interested in your perspectives on this. So there are lots of approaches that multi-robot systems community develops that are specifically focused on certain problems and tries to exploit the structure within those problems as much as possible. And of course, some of these approaches more than others tend to be applicable across a wide range of applications. What is it, in your opinion, that we could do to make sure we are not addressing one-off specific problems? And what are your thoughts on being able to generally incentivize the things that we generally care about, such as efficiency, resilience, and things of that sort across multiple domains?
I'd like to talk about this.
Sure, thank you.
So I dabble in the sense, or I work. I shouldn't say dabble. I work. No, there are areas of research like everybody else where we dabble. We published a few papers, but we don't consider this to be our main thing. But there are two areas and two communities in which I work and don't dabble. One of them is AI, and the other one is robotics. And for those people who are in that overlap between these two communities, see that there's a great difference in how they approach problems. So in AI, if I wanted to draw the stereotypical paper, the paper is about an algorithm and it works in 3 or 4 different domains. And in robotics, if you go to ICRA or RSS or IROS, if you go, let's in fact, let's pick on ICRA and IROS because they, I think, representative more of this. RSS is exactly much more focused on the overlap. But if you go all the way down to the extreme of how roboticists from come to this, then in fact they are focused on a problem and they offer you optimized solution for that one particular problem. So it's very, you would find a session focused on multi-robot coverage. And in AI, if you go to an AI conference, you'll find a session photos focused on a particular algorithm and its variants. And different people will come in and talk about all the different problems they solve with that algorithm. So I think that's the one thing that I actually try to bring as much as possible from AI is that I'm less interested in building a new swarm that can do foraging. I am interested in a mechanism that can do foraging and can do navigation and can do aggregation and can do these other things. And this has, and this is a personal choice. This is not a saying, this is not, none of what I'm saying is says one community is right, the other one is wrong. I'm saying there are different DNAs, to the organizations, to how these communities work. And I think it's a very personal choice. I do think that the more I've done and written papers that focus on a particular problem, the more I became aware of the fact that actually I can't take the solutions from them and make them work on a different problem. And if you care about this, that is, if you want to do, I've had a series of papers on multi-robot coverage and adversarial coverage and so forth. And the one problem, the one thing that was always frustrating to me is that we were making all these great advances, but I couldn't translate them to anywhere else. The coverage was becoming better and was, doing this and doing that, but generating the general lessons from this and where I could take them to a different problem in robotics formations, it was becoming harder and harder to do. And so for me, this is a great challenge is to how to navigate that both academically, these two communities, but also to really navigate the issue of how do you learn from this and when do you stop diving into a problem because you think you're not generalizing enough. For me, because I care about the general issues, I need to stop myself. And for those who actually want to solve the problem is, when do you start generalizing and how do you do it?
Okay, all right, thank you very much. I think Amanda had a few words to say about that. Amanda, sorry, can you unmute?
Yeah, absolutely. So I think it's a great question. And I think part of the answer is that it's not an either or kind of question. I think that on one hand side, it's really important to develop fundamental solutions because those are the ones that guide us when we start tackling a new problem. But at the end of the day, they might not be useful to us, which brings me to my second point which is that I think that what we really do need to acknowledge is that robotics is at least 50% about engineering work. So we're developing systems here. And as soon as you go and try to deploy something onto an actual real world platform, a lot of the work that you're going to be doing is about really finding out how to tune those parameters and what you need to do to that very general bit of code to actually make it work on an actual platform. So anyone tried to use a common filter on an actual platform found out that you actually end up spending days tuning the hyperparameters of these filters. So this would be kind of example of a fundamental general solution that has had enormous impact and guides a lot of people developing new solutions. But at the end of the day, you spend a lot of time kind of figuring out how to actually make it work on the things that we're doing. And so maybe the question is, well, yes, let's continue developing fundamental solutions, but maybe let's give more importance and more value to all the other 50% that we're doing and find venues and outputs for that work so that does not go forgotten, because at the end of the day, there are a lot of applications and lessons learned from the actual engineering work that we can maybe share.
Yes, Gail.
I was wondering, Amanda, so do you see learning as the solution for this fine-tuning? I mean, so when you're saying we should be giving more emphasis to how to, to that process of engineering, of finding out these parameters for the general methods that we use. I mean, because it is very frustrating, right? You sit in front of this robot and you're now faced with measuring all kinds of values, trying to fine-tune your PID controls or your Kalman filters or what have you. And I would love to have a box that's much better at doing that part. So what role do you see for learning in this, or maybe some other technique that you could think of?
So is your question whether we can use machine learning techniques to tune hyperparameters or first principles based approaches?
And I'll explain. So maybe I wasn't sufficiently concrete. So right now, I don't know about how you guys, but right now, we have lots of students coming in, graduate students, who believe that AI was invented in 2011 by a machine called deep learning. And there was nothing that happened before. And then deep learning occurred, and then everything else is now solved. And their only goal is now to try to understand that machine so that they can build their own AI systems. And one of the things that I continuously encounter when we try to work with these students, or when we actually apply machine learning to learning these things, is that the number of examples that you need in order to get the results that you want come out. Just collecting that data and trying to figure out how to use it becomes more expensive than actually spending those 2 or 3 days fine-tuning the Kalman filters or what have you. So if there's a gap, I think it's there. I mean, we sort of understand that we want to automate this, but the machine learning techniques, at least those that are the fashionable these days, seem to be a far fetch from what we want for robotics. That's what it seems to me. I'm asking whether I'm saying it correctly. I'm not a machine learning person. I only dabble. Machine learning is where I dabble.
Okay, I'm very sorry to interrupt. I just wanted to throw in another question that's sort of related, so given the direction the conversation is going. So this question is asking about, should we, in the first place, and if yes, how, should we exploit the representational power of black box deep learning type models? In what role do you see them, if at all any, do you see them playing in the coordination of complex systems?
Can I answer for that?
Yeah, please.
I have to admit that I'm a bit hesitant to use deep learning on huge systems that involve so many robots because of the dimensionality of the problem. I don't think that I can trust the solution that the algorithm would return in that case, and it doesn't have that many guarantees, and it will also be, as Gal highlighted, will be very hard to train. Having said that, I do think that learning can play a role in providing a warm start, some initial solution or a good guess that can be inserted into a more classical approach algorithm and speed up the process. So I'm saying not, instead of using learning as it's on its own, I would take his suggestion and plug it into a different algorithm that I can trust, and maybe this can speed up the process by a significant factor.
Okay. Any other thoughts, whether you agree or disagree?
I can add some input. I mean, I think the classic view of the way to use learning is, I mean, I think as others have described before, but I mean, you start off with a classic algorithm. Typically, they're based on some assumptions about either parameters or models. And then when you get to the real world, which tends to happen, as Amanda was saying before, quite often in the field of robotics, I mean, you go out and you start implementing things. And I think a lot of people start learning things about, perception devices that they didn't know anything about, before. And then they, you try implementing them in the real world and realize there are limitations in the assumptions. Similarly with communication systems, a lot of what happens in these multi-agent problems is you've made some prior assumptions about how well things are going to happen. And when you start communicating, you get in the real world and realize that doesn't work quite as well, or the assumptions are violated. And that's when I think learning can play a role. I mean, you're not doing anything different per se than system identification is sort of the most simple form of it, and then you just do model learning based on that data you collect. But the thing is, if you're trying to do things like communication policies, like I was describing before, and the way we were talking about it in some of the papers I was describing as well. I mean, the point is that the ways that you would assume as a robot team you might communicate ahead of time based on models and assumptions about the way the world was going to be, you get to the real world and realize, no, it's not quite that way. And it's that type of thing that you'd want to revise. And the point is that that policy for communicating is very complicated. And so coming up with any sort of model is going to describe that environment well, and then coming up with a better communication policy, not impossible, but still a very complicated thing to do. So again, rather than trying to learn the model and then predict the policy, why not just learn the policy itself? And so I think that's the role that learning should play. And I think, the caution that was raised by some of the other speakers is that you just, as students, you just don't want to jump right into deep learning. It's like if as often described to my students, if deep learning was the solution, what was the question, right? I mean, and by that, what I mean is, did you really dig deeply into the limitations of the capabilities of the classic algorithms, identify those limitations, and then say, I can't find a way to resolve those within the context of the classic algorithms, then it's okay to sort of switch on a learning algorithm and then identify whether or not it can move beyond what could have been done before. So you don't want it to be the first solution. You want it to be an augmentation to fix a limitation in something that you've understood from the past.
Okay, all right. So now I think we can slightly switch gears. There was a question that was posted earlier, and I think there's another question here, which is along the same lines that just came up. It's regarding the need for benchmarks and data sets. So just for example, in this workshop, we have seen a diverse set of talks. We've seen a diverse set of papers that sort of handle different variants, even many of them proposing general algorithms, but they are applicable to different problems. And everybody tends to report their own numbers of how good it is. And of course, it's compared to other baselines that are very closely related. So the question here is there a need for creating standard tasks that are challenging for multi-robot systems in general? It can be something along the lines of just task assignment, but are there standard benchmarks and data sets we can exploit so that we as a community can agree upon what tends to be the challenges and keep track of the improvements? And do you see a need for that in the first place? And if yes, what are your thoughts on how we can go about doing that? Yeah, please go.
So I began to answer online, and then I'm happy to take this and on the way to apologize because I just sent a Zoom invite from my son's birthday to everybody by mistake, and I apologize. And it would be happy if everybody joins in to say hello, but no, don't please. Yeah, I just made myself into a noob. So I have a love-hate relationship with benchmarks and tests and competitions because I've been on both ends of them. So on one hand, they can be very helpful in promoting research because people can do comparisons and you can do comparative evaluations, and it's much easier to show that your new algorithm or new technique works because it's X percentage higher than anybody else's on a given benchmark, which also everybody else can test. So it can really drive a field forward, and I'm really happy to use benchmarks and tests when they're available. I think it's very easy to also get lost in the competition for better within a particular benchmark and specialized. And the two case in points I'd like to show or discuss in this regard are RoboCup and the planning competition in AI. So RoboCup was very much, remember we talked before about engineering or roboticists and the AI people. So RoboCup from that perspective was very much kind of an engineering mentality in that there's a single competition and everybody competes on that, on the same task, and the task keeps moving, and this is how you push the goal for the task and the difficulty there keep moving forward, and this is what makes the competition or the research more challenging and newer research results, but it's still focused around RoboCup. And I think it generated a lot of excitement and it was fantastic. And I think I still would prefer to have all my students start with this because they see where the real problems are and what the current techniques work. But it also gets you very specialized results. So the fact that you are building something that works well in soccer does not guarantee that you get anything else out of it. And it's very easy to get excited about the competition and lose sight of the bigger picture, which is, can you use that to solve a more, you could still be specialized, but a more interesting specialized problem. That is one that actually helps humanity in a better way than entertainment for robots seeing robots score goals. The other side of it is the planning competition in AI, which was started around the same time as RoboCup, so late 90s. And in advance, what they did was actually work on multiple domains. So the planners that were competing were tested on how well they can solve a wide variety of problems in a wide variety of domains. And for the longest time, I thought that was a much more healthy approach in terms of the science that it was driving. And guess what? They also had a problem. So what happened was that once they publicized the domains, then new papers were getting in only if they could beat previous planners' work on those domains and on those published problems. And in fact, some of the problems and the domains became the object. So when you were trying to push new planners with new capabilities that were not representative of what was going on in the competitions, that is, for example, you move away from classical planning to probabilistic planning to hierarchical planning to planning motions and planning in continuous environment and so forth, then suddenly, you couldn't compete in that planning competition. And as a result, because everybody was looking at saying, well, this is where we test our stuff, it was harder to get papers in. So I think one needs to really look at benchmarks and test with a lot of, I wrote it very briefly in the chat. I think it's a little bit like Tylenol. Right. So if you take a little bit of it, it's fantastic. It makes you feel better. Supposing that your area is sick or it could be better, right? It's a little bit like that. But if you take too much of it, it becomes very toxic.
Okay. All right. Thank you very much. So before we give the floor to Amanda, Dimitar or Vaibhav, do you guys have any thoughts on the stuff we have touched upon? We can get back to other questions later as well.
No, I think most of the points have been covered. Yeah, let's move on to the other questions now.
Okay. Amanda, please.
So only very briefly on that very specific question on benchmarks and competitions. So I just wanted to point out that to some extent, well, I'm a huge fan of benchmarks, and I also think competitions are a great way of advancing science. But one of the things that kind of disturbs me, and this is especially true for learning-based approaches, is that there's a certain conflict of interest when you're comparing your approach to other people's approaches. And again, specifically in the learning community, it really depends how much effort you put into the hyperparameter tuning. So you're going to do a really hell of a good job on your method, and who knows what you do with the other methods. And kind of to conclude this point, I'd really love to see more coming from third parties. So researchers who take code repositories, code that has been made available online, and put together papers actually comparing them and do their best to do a fair job. And I think that's maybe the right way of approaching really evaluating how well the research community as a whole is doing.
Okay. In the interest of time, I think we can probably discuss 2 more questions, but Rajesh, do you want to pick one of your favorites?
Yeah, sure. So, I mean, speaking about multi-robot system, one of the favorite topics that everybody wants to discuss is about heterogeneity. And we had a number of discussion about heterogeneity in this, like Vaibhav gave a different perspective. Gal had a different perspective. So what do you guys think is actually lacking in terms of like quantifying heterogeneity, and how do you actually like really exploit the fact that you can sometimes make the team helpful with heterogeneity, and sometimes it could be worse? Like, what are we lacking? Like, are we lacking some perspectives that we haven't explored already? Like, so yeah, the question is open for the floor.
I think if the question is that how do we quantify heterogeneity? Yeah, I think heterogeneity is already there, right? So any lack of symmetry in system is heterogeneity. So I think the right question to ask is not how to quantify heterogeneity, but to quantify the influence of heterogeneity on performance. And that will answer whether we need heterogeneity or not, right? If we have enough resources all the time, we perhaps don't need heterogeneity. But I mean, if you look at, I'll give you an example of biology because that's where I kind of look at most of the time. So I mean, we could make all the animals leaders, but there are leaders which have very specific role. They have to conserve their resources, and that's why that leadership emerges in those groups. So nature is giving us a lot of examples how we conserve resources by making things heterogeneous. Now that heterogeneity has influence on the performance of the system, and that can be characterized. And for certain tasks, that heterogeneity may not play any role, and for certain tasks, they may have an immense role. So, so I would say instead of trying to characterize or give some sort of measure of heterogeneity, yes, we can do that. But a more critical question is more sort of task specific, and what is the influence of heterogeneity on a particular task that we are dealing with.
Any other thoughts on the?
I will just post a slight addendum to that question. So we all talk about how when you have redundant robots that are necessarily homogeneous in some ways, that promotes resilience, and how you can talk about robustness, that the strength that you get in numbers, right? Of course, having heterogeneity sort of complicates this scenario. And by heterogeneity here, I suppose I'm specifically talking about having different types of robots as opposed to taking a heterogeneous approach to solving tasks. Perhaps Dimitra can expand on this. I'm just curious about how difficult does this problem of maintaining robustness and resilience become when you have robots of different kinds? Do you still need to exploit homogeneity within each group? Or I'm just wondering your general thoughts on that.
Yeah, all these are very good questions. So for example, for the type of problems that I discussed, essentially there is some sort of underlying assumption that every agent in the same team, in the good team, is going to play, for example, the same controller, consensus-based or otherwise. So there is a notion there that we are in the same team and we are all comprising of the same capabilities. So anything that is not falling into this model essentially has to be filtered out or classified as adversarial, so none of the team. But even within, so I think that heterogeneity would dictate different information filtering, different information processing algorithms on how to understand that something that is not similar is of the same team, not adversarial. So that would be probably something that requires further investigation for this type of resilient consensus-based controllers. Another aspect would be, even in a cooperative scenario where everyone wants to achieve the same objective, you might have heterogeneity because of the tasks, because of the sensing capabilities, because of the communication capabilities, as Vaibhav already mentioned. So there the question is to investigate probably is how these differences, how the heterogeneity affects various performance metrics within the team. So for example, maybe considering heterogeneous interactions, like directed interactions, either in communication or sensing, or on which agents you take into account in order to make a decision, can maybe help with maybe accomplishing your objectives faster, or having to compute smaller, to solve smaller problems in order to compute your control action, in the expense of having or on resorting to worse solutions in terms of maybe the path length, or maybe being more vulnerable to undesired local minima in your mission, in your application. So so I think that again, heterogeneity is a matter of being defined in a more application specific or task specific way, and it definitely affects it will definitely affect how we design our algorithms, such that the overall mission can be accomplished in a heterogeneous manner.
Okay, awesome. Thank you very much. I think in the interest of time, we're pretty much almost out of time here. What I would love to do is ask each of the speakers about their favorite or something that they're most excited about in terms of the current open problem. If you had to choose one, I'm sure many of you have many. If you had to choose one, what would be that problem for you? This is perhaps could be very inspiring for people who are just starting out to work in these areas. I suppose we can go sequentially. I will call out a random order based on how your videos are appearing on the Zoom call. Vaibhav, it'll be great if you can get us started.
Sure, I think one of the interesting things that, I mean, we have talked about this, that heterogeneity. I mean, you are given a heterogeneous system, and we talk about how do we kind of design things with that heterogeneous thing, right? I mean, but the lot of effort in biology which talks about these robust and resilient things emerges out of perhaps starting with the homogeneous population, right? So to look at from an evolutionary perspective how the heterogeneity emerges and leads to the kind of robust and resilient behavior, I think that's a very interesting and challenging problem. And to do that in an interesting distributed way is certainly something that I'm very interested in.
Okay, thank you. Amanda, please.
Yes, so I think perhaps for me, the most interesting avenue right now is not necessarily an application, but more of a question. I think that it's not, at least to me, it's not entirely clear what heterogeneity really means and how you formally define that. So as you saw from my second project that I proposed, redundancy in itself was actually not the thing that really provided performance improvement. It was the fact that redundancy allowed the system to exploit diversity. And this really leads to this interesting question of, well, what is the interplay between complementarity, redundancy, heterogeneity? Because redundancy is something that we actually associate with homogeneous systems. So I think really understanding a little bit better what it is that we're really looking for, and perhaps not defining just one foundational new framework, but several formulations of what this actually means is helpful. And equivalently, I think, I saw it in reviewer comments to the papers that we submitted, and I think these are all really, really good questions. Often people, when you propose such a thing as redundancy, the pushback you get immediately is, oh, but that costs a lot. And I'm like, okay, this is a good point, but sometimes it's better to have slack, and understanding when it's important to have slack and what slack and redundancy really means in terms of cost and how you're going to balance that with the, that ultimate metric that you're trying to hit. Maybe that's something that we should think a little bit more about. So efficiency has always been lauded by the academic communities, and we've never really thought about, well, maybe, surviving is better than thriving or something like that. So I think these are interesting questions to me.
All right, thank you. Next, Gail.
Sure. So I think the biggest challenge is really the one that's facing swarms, and we're seeing it here. I mean, the biggest challenge in swarms, I should say, is again this issue of moving from global to local. So automatically saying, here's the phenomena that we want to see, and getting a swarm that will actually do this. Heterogeneous swarms are sometimes necessary to do that, but they're not the goal, right? They're the tool. And I still sense that swarm research, in some sense, has a lot to go on, has a lot to do, and there's a lot to do to go before we can go and declare that we can actually do this. There are fine examples of research doing this. Radhika Nagpal's group at Harvard, for example, and others that have looked at the problem of how to reduce a given task to a swarm so that the roles can actually do this. But I think, there's still a lot. This is the main challenge. If I wanted to do a PhD, that would be the PhD right now, tackling this problem.
Right, thank you. Next, we have John Howe.
Yeah, thanks. So I think one of the questions we've been trying to address is, even with vehicles that have similar capabilities, what is it's sort of handling the heterogeneous knowledge and information that they have, and thus trying to address the questions across the communication network about how the information should be exchanged and why it's being exchanged. And that gets into partly sort of connected to the mission of the overall team. And so the sense of information exchange being mission related, in the sense of why might a robot need to know that extra information, has to do with what they're trying to accomplish. And so thinking about that connectivity between the mission and information exchange and knowledge, then it begins to couple together a lot of really interesting aspects of the planning and sort of estimation part of this problem. But I think as you've seen many people talk about today, I think that the transition from sort of, the academic world of sort of things in MATLAB or simulation to the real world where you're putting things into real life, there's always a lot of good lessons learned there. And I think getting that experience and then sort of going back into the academic world and saying, okay, how can I design these algorithms to function well in the real world is a great way for a student to get involved in the research.
Thank you. Next we have Dimitra.
Yeah, thanks. So, like from my perspective, what I see as a very interesting problem in terms of those big teams that have spatial-temporal behaviors would be how to be able to plan, make decisions, and control against adversaries that might not be just I'm sending you wrong information, but rather I have a spatial-temporal mission by myself. So how we blend in a way, an efficient and probably correct to the extent possible way of these learning algorithms, like deciding which type of learning makes sense for our problems and how to blend it with maybe model-based approaches for which we can have some provable guarantees for the models that we have available. I think to me, this is a direction that is worth pursuing in the years to come. And how to do that in the presence of constraints that come with the mission itself. Like you usually have a finite time horizon in order to make a decision, because otherwise, you will have collided. That's one big problem out there. Or even if, or the question, the other perspective would be, what if I can tolerate the loss of some of my agents? If I have a big swarm, but I end up having the mission, accomplishing the mission with half of my agents, then how can I do that? Right. So these are the problems that I see myself working on in the next couple of years.
Thank you. Finally, we have Kittle.
And the problem I've spent considerable time thinking about is actually not unique to heterogeneous systems, but it also arises even in homogeneous systems. So we know quite well how to find or search for paths in multi-agent systems where we want to avoid conflicts such as collisions. And we also have a lot of approaches for task allocation. But the problem is that in many cases, those task allocation approaches are oblivious to the conflicts that may arise when we're actually executing the solution. So the question is how can we effectively and efficiently perform combined task allocation and pathfinding simultaneously together?
Okay, thank you very much. So I think that brings us to the end of the panel sessions. I thank all of you, all the participants, the invited speakers. Thank you so much for taking the time to prepare your talks, for answering questions, and also the participants for contributing so many questions. I will just remind that the Google Doc will stay online for a while. So please feel free to answer any questions that we did not have a chance to discuss. And of course, feel free to post some more. If the authors or the speakers are available to answer, they will. Thank you so very much again. And I appreciate all your time. It's unfortunate that we all could not meet in person and have these conversations, but I'm happy and thankful for all of you who are trying to make this as interactive as possible. I appreciate that. Thanks.
So thank you guys. Thank you everyone for.
You guys.
Thanks.
All right.
Thank you, everyone.
Take care.
Thank you.
Bye.
Have a
Thank
good
you, everyone.
rest of the conference.
Bye.
Bye.
See you.